astronaut Bagley. I am one of the two partners who owns the space. So this space you're in is a company called Nonfiction, and what we do is that we take science fiction and we make it real. We design everything between brain implants, space modules, wearables, and architecture in Africa. So it's a range. Today I would like to introduce Alder Riley, whom I met actually 3 years ago on Clubhouse. It's a virtual version of these events, and he'll tell you a little bit more about it. But today we are very privileged to have Dr. Frick do a presentation on off-world manufacturing of semiconductors. Alder, amazing.
So, hello everyone, I'm Alder. I'm the person that's been pestering you on Twitter. So this event is, this is our second in-person event. So thank you so much for taking a chance on very new event organizers. So this is our second one of these. Small steps and giant leaps to the organizing community of this. About 100,000 members spread off across a bunch of different platforms, mostly on Clubhouse, but on Twitter and all the other cool things. Aside from that, I run a 3D printing startup. We make factories that you can drop ship anywhere. But honestly, I'm more here because I'm so thrilled that you folks are here. People should be excited about space exploration, and not only just excited, but actually doing things about it. One of the great things, you guys all, or folks all filled out that questionnaire. One of the great data points out of that questionnaire as results is that one out of every two, so 50% of the people in this event, in this room, have had direct work in the space industry. So, if you're curious, if you're a job seeker, if you're an investor, whoever you are, look around, meet cool people. But before we do that, Jessica. Jessica has provided me a wonderful intro, so I hope you'll forgive me reading it off, because I did not memorize it.
It's really long.
Dr. Jessica Frick is a research engineer in Extreme Environment Microsystems, in the Extreme Environment Microsystems Laboratory, XLab, in the Aeronautics Astronautics Department at Stanford University. She received her Ph.D. in Chemistry and Materials Science at Princeton University in 2019. As a National Science Foundation Research Fellow, Dr. Frick developed bulk crystal growth methods using Bridgman Technique to grow wide-bandgap WBG semiconductors. Merging her professional expertise into semiconductors and advanced materials with her passion for space, I think we can, just space, passion for space. Dr. Frick has evolved into an emerging leader in the field of microgravity semiconductor R&D. Dr. Frick and the XLab have an array of ongoing ISS investigations, annealing WBG semiconductors in microgravity using low gradient furnace in the Materials Science Research Rack, MSSR, launched on SPX 28. Hydrothermal synthesis of graphene hydrogel using the SUBSA furnace in the Microgravity Science Glovebox, MSG, launched NG19. And crystal growth in metal organic frameworks, MOFs, in microgravity, TBD 2024. This presentation will include scientific benefits of semiconductor crystal growth in microgravity and how these benefits can create value in the global semiconductor supply chain right here on Earth. Dr. Frick will also review professional recommendations resulting from the March 2023 workshop she co-organized at Stanford University on semiconductor manufacturing in the space domain. So, with that, Dr. Frick.
All right, so I am getting a little bit of feedback that online the audio is a bit off. I think we might want to check that before I start.
We will be doing a high definition version of this recording afterward.
Oh, perfect. Okay. All right, well, thank you so much for the introduction and for organizing this event, Alder. I really appreciate it, and also thank you to our hosts. This is an incredible space. I've never been here before. There's a lot of cool things that I definitely want to check out later after the talk. So today I'm going to talk about catalyzing the in-space economy through existing terrestrial markets. And I wanted to first start off by mentioning the fact that we have a little over 40 years to establish a spacefaring civilization. And this is based off of the 2015 publication from JPL, which defines spacefaring civilization as an economically profitable space-based economy. And why I'm telling you this is not to scare you, but rather to get across the sense of urgency for us to kind of act now and get the in-space economy going. Because considering what's happening with natural events in the world, available energy, and human tendencies, now is the time to act if we want to be a spacefaring civilization, or else it's going to be soon too difficult or impractical to pursue. So I think all of you in this audience can agree that this is kind of the near future civilization that we're looking for. So this is put together by, the video is a bit off, but by Eric Kulu here, who runs the Factories in Space website. And this is a vision of a self-sustaining in-space economy to support the future spacefaring civilization. And this includes LEO, but also habitats on the moon, Mars, asteroid farming of resources, and other rovers that can access the lunar surface, Mars surface, etc. So moving on, how are we going to really get this in-space economy going? Because it doesn't actually exist. This is a great future picture, but it is just in our imaginations right now. So how are we going to kickstart the in-space economy? And it is many professionals have the opinion that one of the ways to do this is by leveraging our existing terrestrial economy. So for some products, the benefits of making them in space and selling them on Earth actually outweigh the cost of in-space production. And that's exactly what this white paper was all about: semiconductor manufacturing in low Earth orbit for terrestrial use. And so in this white paper, we made the argument that semiconductors are a key product whose production in space will enable us to leverage an existing terrestrial market to fund or kickstart the in-space economy. So let's dive into the white paper a bit more. And what I like to do when I'm giving a talk is to really dissect the title piece by piece so that we're all on the same page. So we'll start with LEO, so low Earth orbit. Low Earth orbit, what we care about really in LEO is the microgravity environment. And so there are also other perks which include free vacuum, solar energy, low environmental impact location, but what we really are after is microgravity, and LEO is the closest access point to this outside of Earth's atmosphere. And so why we care about LEO is because there are physical phenomena in microgravity that affect the behavior of liquids and gases at the macro and atomic scale. So these physical phenomena include buoyancy and sedimentation, container interactions, hydrostatic pressure, and thermal convection. And on Earth's gravity, these phenomena are turned on, but in microgravity, these are turned off. And so there's explanation in the white paper on this, but just to give you a brief example for buoyancy and sedimentation, if we have a liquid body and we throw in heavy objects and light objects, the heavy ones on Earth will sink and the light ones will float to the top. But in microgravity, if we throw in heavy and light items, theoretically they will disperse homogeneously throughout the liquid. So moving on, let's talk about terrestrial use. So again, that brings us back to this kind of graphic here where the benefits of producing these materials in space outweigh the cost of production. And so what I'm talking about here is kind of a closed loop system where we have access to raw materials on Earth now. These can be shipped up to low Earth orbit where they're processed into products. These products are brought back down to Earth, and then they're further manufactured and sold as products. So now let's move on to semiconductor manufacturing. So in order to understand this, we really need to review the manufacturing stages in the global semiconductor supply chain. Because it is a very long process to get a crystal, which is the first step, all the way to your cell phone, right? So the very first step, again, is growing crystalline ingots. And these are massive. These boules are the size of a LeBron James in height and then also in width as well. And then once these are grown, these are sliced into wafers for substrates. And these wafers, they can range from size of little CD-ROMs to vinyl discs. And then after these are sliced into wafers, they go to companies like Intel, for example, where circuits are patterned on them and they're diced into these little square chips. And then the little square chips are packaged into a device. So this is your semiconductor device here, and these can be on the scale of a penny or even smaller. And then you take all of these together and you assemble it into a product, so your iPhone. So it's fun to always look at this and imagine, you know, all of the components that went into building this device, and we're all carrying around little silicon crystals in our pockets. So what steps really scientifically and practically benefit from processing in space? Because I'm guilty of this as well, but many people use semiconductor manufacturing as a catch-all term for all of these steps. But again, each of these steps is very important and very unique in and of itself. So which ones benefit from being processed in space? Working our way backwards, the integration step, that's probably not practical or scientifically beneficial. If we look at these kind of middle stages here, the fabrication stages, there are some R&D studies that point to yes for some aspects. Our colleague Curtis Hill at NASA works with Intel on doing some of the circuit patterning, but there's a lot of R&D still to be done, so we're not really sure about this part yet. But what we do know for a fact is that this very first step, the crystal growth, does have scientific and practical benefits of being produced in space. And let us go a little further into understanding exactly what do I mean by scientific and practical benefits. So again, what is it about space, what is it about microgravity that really makes growing these crystals in that environment beneficial? So we're going to learn about cadmium telluride as a case study. And cadmium telluride has been grown in space probably about 7 to 8 times, starting in the 80s. And here's just a sampling of those reports. And for those in the audience who aren't aware, semiconductor crystal growth has actually been happening in space since 1973 on the Skylab mission. So cadmium telluride was chosen for many of these studies because it has an existing terrestrial market actually in the billions. So cadmium telluride makes photovoltaic devices. So it makes solar cells. So this is a component, layer by layer component of a solar cell, where the key component here is this cadmium telluride crystal. It has a zinc blend structure. So anyway, this was chosen because it has a huge market, huge, I guess, applications on Earth. So as a crystal grower myself, there are a few different types of physical properties that you look at when you're comparing crystals to see, look at the quality and kind of compare them. And that includes the defect concentration, dopant content and density, and crystal size. And so to spare you the details, if you parse through all of these studies, the conclusions are that the microgravity grown crystals have 10 to 1,000 times fewer defects, they have a uniform dopant distribution, and they have a 2 to 3 times increase in crystal size. Now for me, as someone who grows crystals, this is really incredible work, and I would just publish this and be super happy. But this probably doesn't really mean anything to people in the audience or anybody else along the semiconductor supply chain that I mentioned. And so what we're going to do now is a little exercise to kind of translate what these benefits do later on in the semiconductor supply chain. So what are these, the fewer defects, uniform distribution of dopants, and increasing crystal size. What benefits, what is the value creation later down this line? So let's start by, again, kind of looking at our process of going from a crystal ingot to wafers. So if we are growing a crystal on Earth, this gray here represents the usable volume of that crystal boule, because you have to actually cut off the top and the bottom of these ingots because they don't have the right quality, they don't have the right dopant concentration that you want. And so I'm being pretty generous here by saying you can use around 80%, but that really just depends on the type of material and the size of your boule as well. Now, if we consider what we just talked about, that the crystals have 10 to 1,000 times fewer defects and a uniform dopant distribution, this means that the usable volume of that boule increases to greater than 90%. And so we have an increase in 10% of usable volume. So we can get more wafers per boule, is what I'm saying. Now, if we continue with looking at the 2 to 3 times increase in crystal size, this means we're going from something of x diameter to up to 3x diameter. And so we're going from something that, for example, could be a 2-inch wafer up to about 3.5 inches. And what this means is an increase of area of 100 to 200%. And so if you're going from, again, my example, 2 to 3.5 inch diameter wafer, that's an increase of about 6 to 7 times more chips per wafer. So if we kind of add this together and look at the end product here, combining these two values, that means product-wise we have over 150% increase in product. And that's not even mentioning the fact that because of the fewer defects and the uniform dopant distribution, you also get perks like extended product lifetime, increase in solar efficiency, and wider operating ranges. So with that, I hope that it makes a bit more sense, and we understand now the value creation going from growing a crystal with all of these really great benefits all the way to an actual product. But, and I was actually just having this conversation before the talk, we really don't have any experimental data for these values here. These are, again, kind of extrapolations based off of real hard data we get from the crystals, because again, since the 1970s, when crystal growth was done in microgravity, it's really crystal growers who are reporting on these. So they grow the crystal, they get it back from space, they analyze the data, they publish these results, and then that's it. But what we really need to do is take these crystals and put them through the entire supply chain to get quantitative values for these benefits. And so what I'm saying here is that the field needs more quantitative value creation studies in order to convince the terrestrial market, i.e. semiconductor corporations, to invest. Because it's interesting, I don't want to go off on too much of a tangent, but the big companies like an Intel or Samsung or Infineon, for example, they don't do crystal growth. They buy all of their crystals from China. And so when you're trying to tell them, hey, look at these great increases in benefits of these crystals grown in space, they're like, oh, we don't really care. Show us the data of the actual device, our actual product. So I just wanted to point that out, and we can talk about that in the Q&A. So anyway, the point is, because of this, we decided to put on a workshop at Stanford, the Semiconductor Manufacturing in the Space Domain workshop, which was co-organized by XLab members Jasmine Cox and, of course, our lovely PI, Professor Debbie Sineski. And we came together with academia, the space sector, the semiconductor industry, And we asked the question, okay, how do we achieve more iterative data to de-risk investment to make in-space manufacturing for semiconductors a reality? And we had, again, over 100 people in attendance at this event from all over the space sector and semiconductor industry and academia. And there were 3 key areas that the attendees kind of determined that we need to strengthen. So 1, infrastructure, 2, funding, and 3, ecosystem. And really the ecosystem is the key here because once we have an ecosystem set up, the funding and infrastructure really grows from that because our industry is nascent. There isn't really a home for us because we don't really belong as someone with a crystal background in the organizations that focus on satellites or CubeSats, for example, because those can't do the transformations that we're looking for. And we don't necessarily belong at, you know, an American Chemical Society or American Physical Society, and so we need our own home. And this is super important because this will enable us to, again, prioritize, so determine what semiconductors we should be focusing on. Is it cadmium telluride? Is it something simple like silicon? Or is it something more exotic? This would enable us to advise. So I cannot tell you the number of times that Debbie and I have been contacted by space companies saying, what kind of infrastructure do you need? Tell us what you need. So this will be able we'll be able to actually kind of bring the community together and say, okay, this is what we need. We need this amount of power, this amount of space, and on this timeline. It will allow us to connect. So again, bring together the relevant communities. And because there are a lot of folks in academia who might be interested in actually doing research, but they just don't know where to start. Sharing, so that's another big thing, hosting databases and conferences to connect. I cannot tell you how crucial this is, and actually a database, we can get into it in the Q&A, but that was really the start of the whole workshop. And then translation, so kind of walking us through that simple process that I just did with cadmium telluride, but we need to do that with way more materials. We have about 160 to get through. So there was also an additional recommendation from the attendees, in that the ecosystem should include other advanced materials. And by advanced materials, we mean a materials group that requires extreme process parameters, so high temperatures, high pressures, toxic chemicals. So semiconductors are a type of advanced material, and they're a materials class, but it also includes things like metal alloys, high entropy alloys, and superconductors. All of these require the extremely high temperatures, pressures, and toxic chemicals during their synthetic processes. So, and then all of these have kind of overlapping applications too in electronic devices, which we focused on today, but then also in collectibles, so jewelry and gemstones, infrastructure as well, and also quantum technologies, so things like quantum computing and spintronics. So with that in mind, the follow-up to this workshop is actually launching an institute, the Institute for In-Space Manufacturing of Advanced Materials. So we are a nonprofit whose mission is to inform stakeholders, educate the community, and create collaboration between academia, industry, and government to accelerate in-space manufacturing of advanced materials. And our aim is to leverage existing terrestrial markets to catalyze the in-space economy. And so again, just like the points I hit before, the market report is going to be one of the big outcomes of our institute. So people want to know what is the value creation, and so kind of walking through that exercise I just did, but even more in depth. A database, as I said, we need a place to host all of the microgravity studies, but then also subsequent terrestrial studies after those crystals come back to Earth. So we're also planning on putting together a webinar series, an educational series, and this is not for K through 12 or undergraduate or graduate students, but this is really for people in companies that are curious about microgravity. And we want to really target people, executives and people in the C-suites, to really understand how microgravity can be used as a tool to help their product line. We'll also have a road mapping event to determine what semiconductors we should focus on, and then after that, what materials, maybe superconductors, maybe high entropy alloys, we'll see. And then also, as I mentioned before, a recommendation report to be able to tell the space industry this is the infrastructure we need, and also to tell funding agencies this is the funding level that we need to make this happen. And we are putting together our governance, and this is kind of a sampling of it so far. So our management entity is Nexite Group, who actually helped us put together the workshop back in March. And Nexite Group is a company who they help stand up institutes. So for example, there was a recent new Manufacturing USA Institute, Simani, that was stood up by Nexite Group. So we are working with the best here. We have an incredible suite of advisors here, not only people who are in the space industry like Phenom and academics, our collaborator Professor Roy Maboudian and Roger Howe, but we have space infrastructure. So we have a Mullick from Orbital Composites. And then we also have people in the materials industry. So we have Dr. John Chen, who is the Director of Technology at Silfex. And Silfex is one of maybe 5 companies in the US that actually do crystal growth. So it's pretty incredible to have him on our advisor board. And then we have Dr. Todd Youngkin, who is President and CEO of the Semiconductor Research Corporation, where he leads about $100 million per year in global research agenda for semiconductors. So he's a big deal. And in our executive committee and staff, our staff is led by Mel Anton from the Nexite Group. Shout out to Mel, who is online. She has been our right-hand woman on getting the workshop together and the white paper out and even this presentation together. And then we are having Gary Rodriguez lead the executive committee. So he is formerly from IBM. He spent 16 years there as the VP of North American Sales. And then after that, he had a career at the ISS National Lab. And so he's really just the perfect combination of semiconductors and other advanced materials background plus space. We have government liaisons that we're bringing on board. So one, I mentioned Curtis Hill from NASA, who's working with Intel now. And we're also in talks with individuals at ISS National Lab, Air Force Research Lab, and Space Force to serve as a government liaison. And then, of course, we have our board of directors, which is myself, Professor Debbie Sineski, who leads the XLab and is one of the world leaders in microgravity research right now on the ISS, and Professor Ann Wilson from Butler University, who with her army of undergrads has put together a fantastic database to get us started. So with that, I want to give you our ask. So we are requiring $750K for the first 2 years, and this will get us the market report and database going, with the market report focusing first on semiconductors as a pilot case. We'll also give a recommendation report for semiconductors to the space infrastructure, and then, of course, our webinar series and road mapping. And we'll be doing additional fundraising opportunities from the government and other foundations. And then we plan to have a sustainable funding model in future years, starting in year 3 or 5, with a tiered membership model. And this is a QR code to our beta site here. It's a little cut off, but hopefully it works. Perfect. So I'll put this back up after my last slide, but so I'm going to end here and ask you to join us. So we're really excited to catalyze the in-space economy through leveraging an existing terrestrial market. And the first thing you should do is subscribe to our mailing list using this QR code here. And then this will keep you up to date on the upcoming info session we're going to have, so you can learn, I guess, where your dollar is going when you donate to our nonprofit. And then we are planning to have our first webinar episode in the next month or so, which we're going to call Microgravity 101. So I really hope you all enjoyed the presentation, and I think I am about on time in the 30-minute mark, so perfect. And yeah, so I can end here. Thank you for your attention, and I'm looking forward to chatting.
Dr. Frick, this was incredible. Let's give her another round of applause. So we've got half hour for question and answer. Well, first things first, hands up. Who's got a question? Or am I going to be the first person? Oh, there we go. We got some brave people. Back.
Yeah, so at the beginning there was this paper with we have only 50 years time. It's because of satellites or trash basically in outer space, or why do we have only 50 years?
So there's a variety of reasons. I would encourage you to check that out yourself. I think if you just like Google 50 years to become a spacefaring civilization, there's more details, but it is a combination of the amount of energy that's left on Earth, and then the kind of global problems that are taking priority. So it's not very practical for us to, go elsewhere, but there's a combination of reasons.
Okay. I'll ask a question.
Yep.
So tomorrow or the next day, Starship may or may not be launching. Is there an impact that an increased amount of mass to orbit has on the ability for this?
Oh, absolutely. Yeah, no, we're really looking forward to that because, again, more mass. I mean, there is already a struggle in the industry to get up the amount of mass, amount of research that needs and is in line to go up in orbit. But especially coming back, I think that that's the most important because we can, shoot CubeSats in orbit all day, but are we getting any actual, physical experiment data back from those? No. And so we're really looking to push that forward in the field is the return because, again, for this, in space for Earth, production to really happen, we have to get them back. So.
Other questions?
So for those of us who work in the space industry, sometimes it's very difficult to kind of welcome the people who are not in that space and make them understand the value of space development. So how would you talk to someone who knows nothing about space, who knows nothing about semiconductors, and explain to them the value of the work that you're doing?
Yeah, that's a great question that I do not have an answer to. I'm still figuring that out, to be honest, and that's something that I need to work on.
Next question. Oh, yes.
Yeah, I noticed your partnership at the conference that you had at Stanford with Blue Origin. Obviously, we know there's a timestamp on the ISS, right? We know that obviously we started out with 4 contracts for the next ISS. Now it's whittled down a little bit, right? Did they get involved? I'm curious how that evolved with you guys with Blue Origin, Orbital Reef, right?
Right, yeah, so the workshop was in part sponsored by Orbital Reef, and they really like to make that distinction because Orbital Reef is kind of a joint effort with other partners like Redwire Space and Sierra. So that started that partnership because Orbital Reef is interested in, what is going to go up there inside their space station, because right now they're trying to, get support to put their station in space, but what's going to go in it is it's going to be this big empty kind of warehouse, but we need to do something in it. And so they are very interested in looking at semiconductor manufacturing or crystal growth for one of those options. And I do want to point out that you had said that referring to these new space stations as the new ISS. That's actually not the case. They're commercial LEO destinations, and there's an important distinction there because I think those in the academic community are a bit worried what's going to happen when the ISS comes down, because if the ISS is replaced with CLDs, the CLDs, of course, are for-profit institutions, and so they don't, we're just worried about what's going to happen for academic work that's sponsored by the government. So,
how long would 750 last you?
2 years. So yeah, I can go back up to that, or not. There we go. Yeah, so 750K for the first 2 years, which again is going to use semiconductors as our pilot case here to create a market report, curate the database, and the recommendation report, and then after that we hope to raise, again, government grants, and then we'll have a sustainable funding model that's based off of tiered membership.
You went into the yield benefits of growing crystals in space. I'm interested in the capability improvements that you get. So are there things that these chips grown in space can do that terrestrial ones cannot?
Yeah, so that's a great question, and I will go back to that slide where I mentioned that. So again, yes, we kind of focused on the yield here because this is the, I think, I don't know if this word is great, but the easiest thing to kind of extrapolate to based off of the real data we have. And we can say based off of predictions that, again, we could get these benefits, extended product lifetime, increased efficiency, based off of having fewer defects in our crystal. So a higher quality crystal will give you a higher efficiency device. But again, we are kind of stuck in the industry just figuring out how really does that translate, because we don't have those experimental studies yet.
Even though you've been growing it in space since the 70s?
Yeah.
Wild.
Yeah. Yeah, so that's a big issue right now. So.
Over here.
About ballpark, how much do you think it would cost to run, for example, one experiment in space?
One experiment in space. So let's see. Whew. So the average grant that is given out through the ISS National Lab is around $300K, but that goes towards, some of it goes towards the researchers at the universities. But then that $300K is matched to about $300K given to the implementation partners who help put that together. So that's now $600K. And then in addition to that is the cost of putting it on a rocket, launching it to space, and then all of the astronauts' time, and then the return. So I would say very conservatively $1 million per experiment right now.
Do astronauts charge an hourly rate?
Yeah, they do. Mm-hmm. I don't know what that is, but.
Really high.
Yeah.
Further questions? Yeah.
So many questions. I'm interested in the high volatility alloys that you were talking about.
The high entropy alloys,
High entropy alloys, yeah.
Yep.
And just more information on high entropy alloys and also superconductors as they relate to quantum computation.
Oh, sure. So I will, so high entropy alloys just means, I'll start with metal alloys because those are kind of the base. Metal alloys are two to three different types of metallic elements, and high entropy alloys are 5 or more. And so because of all of these different elements that make up the alloy, they are called high entropy, and they don't have actually a rigid crystal structure like one would imagine, like I showed for cadmium telluride. And so that gives them really exceptional properties, like insanely high mechanical strength. And so for infrastructure building, that is actually really interesting. But again, they're very difficult to make because of the high entropy of these materials. And then superconductors, to be honest, I can't really answer that question that you had there. That's beyond my realm of purview, but there is, all I know is that superconductors do require the same amount of, again, high temperatures, pressures, and toxic chemicals that semiconductors, metals, and high entropy alloys require. And sometimes superconductors actually are semiconductors, they just don't superconduct until low temperatures. But this is a great question, and I'll get back to you.
So, great talk. I have two questions. Is there a market for producing these semiconductors for space as opposed to bringing them back for terrestrial lab?
Yeah, so there are some materials that are used. For example, the ISS uses solar panels, and they're always the astronauts are always working on on those solar panels there. So that's one aspect. But I think that it could be part of the institute and aiming for use in space of these materials. But the big money right now is going to be taking them and actually using them in the larger markets on Earth. Because again, in space, for space is really the goal, but it's just not big enough right now.
Then my second question is cost, right? So, there's a payload cost of launching materials to space, raw materials. What's the cost of bringing them back?
That's a great question. So again, that's the biggest part, as I mentioned before, is getting them back. And so when we do kind of our rough estimates, we calculate what it's going to cost to ship up the raw materials, which is based off of weight. I think that the going rate is like $900 per kilogram. And then for the return, we do double that. Mm-hmm.
For looking at the timeline again, going back to that, with the timeline given that we're going to be, obviously Artemis is a big priority for NASA, right? And 2028 is kind of the timestamp. We know that, we'll see.
We'll see, yeah.
But we know we want to do multiple settlements on the moon. Do you think that, probably it's more pristine in microgravity, but do you think that there's maybe more permanency if you did growing the crystals on the moon? I know it'd probably be less yield given the gravity.
Right, yeah, so that's a great question. So yes, the moon is interesting because if we go back to this figure here, you can kind of imagine, if we're able to access a lab on Earth, in Leo, on the moon, those are all different gravities. And so you would be adjusting them just like you would temperature and just like you would pressure. It's just another knob to turn on your material synthesis. And perhaps for some of these materials, the gravity is more, we're looking for a lunar gravity. It works better. Or maybe there is a trade-off between, it is better in microgravity, but, it is giving us, the lunar gravity is better than Earth, and there's some trade-off there. But that's a great question, and I think that one that we'll look into in the future.
Yeah, there's a little bit more real estate on the moon.
Yeah, for sure.
I just had a question then. So if you could vary gravity as a free parameter, would that be useful? So spin something up and spin it down?
Oh, for sure. Yeah, that's definitely interesting. So just going back to my previous comment, if we could just, the ideal case would be, we could have a furnace, but have it be gravity and then just tune that to what we need. But yeah, that is yet to be seen.
So there is an old report, actually, I think it came out of Russia, where they tried to, under very high magnetic fields, like modulate the gravitational forces in the liquid. So, but unfortunately, there isn't much information beyond that. So there was some interest, I think, maybe 30 years ago.
Yeah, and I think vast space, like their goal is to have, I attended a talk recently as part of like a NASA lecture series, and so vast space is they want to put a station in orbit that has different levels of gravity, and that would be interesting for experiments, yeah.
All right, a couple more. Yep.
I remembered hearing maybe 5 years ago about a planned, I don't know if they actually followed through on an experiment to try fiber optic, like the
Oh, yeah.
to make the actual optical fiber.
Z-bond,
yeah.
yeah.
More on the crystal growth side.
Yeah.
Making like high purity optical fiber in space. Is that still like an active field of research?
So yeah, you're talking about Z-band, and that's an optical fiber, and yes, it's very, very similar. I mean, I didn't put it on my little map there, but that is considered, an advanced material where you're getting the benefits of the crystal growth in microgravity, so you get a higher quality optical fiber. So right now, that field, it still exists, and there's a few companies like Upsidal who are focusing on that, but right now it's kind of difficult to do manufacturing scale on the ISS. The ISS is really just kind of a small scale laboratory for R&D, and so we're really looking forward to those CLDs, the commercial LEO destinations, to up the manufacturing capabilities.
All right, one final question. Oh, there we go. Yep.
You mentioned building a database a couple of times.
Yeah.
I was just wondering, what's in the database?
Yeah, I'm using that term loosely, I guess. So it is very difficult, and those in my field can attest, to find any information of the studies from the 70s, the 80s, from NASA, and theoretically it's all publicly available because it was government funded. But I have spent very long nights on the Internet Archive looking at photocopied documents. And so putting that all, so we have a very niche field here, and it's very difficult to find all of that. And then also, I guess, classifying the different types of experiments that happened and on what space station, because that really is important, because different space stations, there are different variables there that you need to take into consideration when you're doing, you're extrapolating value creation from that. Also, there is a lot of Russian work and Chinese work that has been done that, again, is very difficult to find. And so what I mentioned before was Professor Ann Wilson at Butler University. They had a grant where she could put a team of her undergraduates to work just looking for the data and putting it all together. So that study was actually really paramount to, again, the workshop being put together and where I am right now. So.
All right, with that, another round of applause for Dr. Frick.
Yeah.
And a quick round of applause for the wonderful folks with nonfiction. Dr. Frick, you're going to be sticking around for a bit?
Yeah. Mm-hmm.
Awesome. So, and then, finally, another round of applause for Dr. Frick.
Oh, thank you. Yeah. And I will leave up the QR code, if I can get there, just for you all to check out our beta site here.
Perfect.
Yeah.
And there will be a high-definition version of this talk if you missed any portion of it or just want to revisit something. That'll be posted online after this event. Yeah.
Thank you.
Thank you. Enjoy.
Yeah.